Thank you, Fabian. So our next speaker is Cody Finke. Cody is the co-founder and CEO of Brimstone Energy, which is looking at the industrial decarbonization of cement and other commodities. Cody has a PhD from Caltech in environmental science and engineering, and is currently a part of the Cyclotron Road incubation program at Lawrence Berkeley National Lab here in California, where he's continuing to develop Brimstone's technology. So Cody, go ahead and take it away. I assume you want me to share the slides.
Yes, please, Neil.
Yeah.
I think, or is it possible for me to share?
What did you say?
These are the old slides. Is it possible for me to share my screen?
This is the old slides. I thought I updated them.
Yeah.
Okay. It's fine with me.
All right. Let's do it. So, okay. Hold on a second here. Okay, can people see my screen? Great. All right. Thank you very much. So really excited to be here. I love, obviously, native emission technologies are incredibly important. We can't get back to pre-industrial levels without pulling the CO2 out of the atmosphere that we've put there. So today I'm going to talk about the special challenge of industrial emissions and ways that we can make industrial emissions negative. And something that's really important to me is doing that in the absence of a carbon tax, because I believe, as I think everyone probably in this room does, the climate problem is urgent, and governments in general have shown a lack, well, at least where I come from, the United States, have shown a lack of political will towards, really strong policies. And the reality also is that we really need worldwide policies in order to get there. So if we can figure out ways to be negative emissions without a carbon tax in a way that's actually profitable, then we could potentially get there as fast as we need to. I'm going to talk about my company, Brimstone Energy, and what we're doing in that space. So first, little background. So industrial emissions, talk about emissions by sector. Industrial emissions are the largest category of greenhouse gas emissions, about 32% of global emissions. Basically broken down into four categories: emissions from electricity, so that's generating electricity from fossil fuels, which I think could be eliminated by technologies like Fabian's. Non-electricity energy, so this is basically burning fossil fuels to make heat, to heat chemical reactors, as well as engines that directly take diesel or gasoline fuel. About 25 of the industrial emissions. And then the biggest part of industrial emissions are called process emissions. And that's something that I'm particularly interested in. So here's a little slide to describe what process emissions are. So process emissions are greenhouse gas emissions that are a direct result of the chemistry used to make products. They typically don't really have much to do with energy. So the big four process emissions, which are responsible for most of the process emissions, are the production of aluminum, the production of hydrogen, which is an industrial chemical. I know there's a lot of talk of it being an energy carrier, but today it's an industrial chemical. The production of steel, and then the production of cement. So in general, about half of the emissions from all of these processes are process emissions. So here in the graph, on the y-axis, we can see process emissions in petagrams of CO2 per year, or gigatons, same unit. And then here's the four big categories. I've also added the total emissions from total worldwide emissions from airplanes, just for a reference frame. So as you can see, especially steel and cement, the process emissions alone are responsible for enormous amounts of greenhouse gas emissions. One of the things that I'm going to argue today, or show it's possible, is that it's possible to design a chemical process to make these products that actually has negative process emissions instead of positive process emissions. And when you have negative process emissions, that means that we can continue using our cheapest forms of energy, which are typically natural gas and coal, in order to make heat, which we can do for a while until the government catches up and allows us to and regulates renewables. But we can still be negative emissions. So just for background, so I'm going to talk about cement, because what my company makes is cement. And when I talk about cement, I mean we make ordinary Portland cement. We make the exact same cement that's on the market today. Part of the goals of our company is, in order to be fast, we can't be working out regulatory hurdles. So our product is identical to what's on the market today. So this is an image of how cement is made today. There's the normal, very CO2 intensive process. You start with limestone, which is calcium carbonate, and clay. You grind that up to a powder, and you heat that up to over 1450 degrees. When that happens, this chemical reaction happens in the upper left, where limestone decomposes into lime and carbon dioxide. And these are the process emissions. Right? The other fraction of the emissions, of course, are heating the kiln, and the combined emissions represent the combined emissions of cement, which is about 5.5% of global greenhouse gas emissions, about the same as cars. So out of the kiln comes called ordinary Portland cement, or Portland cement clinker. That's mixed with supplemental cementitious materials. So supplemental cementitious materials, well, it has got some regulatory attention. It's actually a byproduct of burning coal, which means that both of these materials that go into making cement are very emissions intensive. So the whole cement process is a very emissions intensive process today. So now I'm going to describe our process. We do things a little bit differently. So I'll say here, so one of the things that we noticed is calcium oxide is the key component of cement, of course. And the problem with the CO2 emissions is we've chosen a source of calcium oxide that is bound to CO2. What we can do in our process is start with a calcium silicate. So a rock that has a lot of calcium in it, but doesn't have any CO2 bound to it. We go through a proprietary leaching process, and what comes out of this leaching process is calcium oxide, as well as amorphous silica, so supplemental cementitious materials. And then the waste products, so any other oxides that are in the rock, which typically are magnesium, aluminum, and iron. We then put the calcium oxide in the kiln, just like the normal cement process. What comes out is ordinary Portland cement clinker, as well as conventional supplemental cementitious material. We mix those two together and make the exact same cement product that is made today. We then recycle our leaching agent, so there's no net consumption or production of the leach agent. And then finally, if there's high magnesium contents, which typically there are in any rocks that contain calcium, the waste product magnesium dihydroxide, or brucite, will naturally carbonate, which means there's nothing we can do about this carbonation. However, if we scrub our flue gas, which is typically already regulated because all flue gas contains SO2, so you have to scrub it. And if we put our flue gas through the scrubber, just like we normally would, we'll make an enormous amount of magnesium carbonate. In fact, it turns out that per ton of cement, a typical rock will actually have 620 kilograms of CO2 of negative emissions capacity. So this is a graph showing the emissions intensity with kilograms of CO2 per ton of cement on the y-axis. And then on the x-axis, we've got 4 different categories. So the first is, this is conventional cement. So conventional cement, the emissions depend on whether we use natural gas, which is a total emissions of about 700 kilograms CO2 per ton of cement. Or if you use coal, you have a total emissions of about 900 kilograms of CO2 per ton of cement. Now, cement will naturally carbonate. So over about a 40-year lifetime, it will suck some of the CO2 back into itself. So the lifetime emissions are closer to 300 to 500 kilograms of CO2 per ton of cement. Now, with our process, we start with carbonation of the waste magnesium. So if we use natural gas as energy source, just the carbonation at the plant gate is already negative 110 kilograms of CO2 per ton of cement. For coal, we're a little bit positive at 250 kilograms of CO2 per ton of cement. However, our cement, again, being the exact same cement, will still carbonate. And over a 40-year lifetime, we will suck the same amount of CO2 out of the atmosphere, in which case both coal-fired and natural gas-fired cement will have a lifetime negative emissions. And the one thing that I argue and say we actually have intellectual property at our company on is all of these rocks that contain magnesium and calcium also contain aluminum and iron. So you can make all of these products from these calcium and magnesium rich rocks. And if you design your process properly, you can actually have calcium and magnesium as waste products, which will allow for negative emissions technologies in a profitable sense. So we work in the United States, and we've started mapping some locations of these calcium-rich rocks. All of the circular dots are known deposits of calcium-rich rocks. As you can see, they're very abundant. These calcium silicate rocks are among the most common rocks on the surface of the earth. So there's a large potential to make this product. And then the last thing that we say is, because we co-generate both the supplemental cementitious material and the ordinary Portland cement, we can actually operate at a lower price point than conventionally produced cement. So here's some of our cost modeling. So here's on the y-axis, we have the levelized cost of cement in dollars per ton, and on the left we have the conventional process for making cement, and on the right we have our process for making cement. So one of the big things is that the co-product, supplemental cementitious material, it's declining in the world. The supply is declining because natural gas is getting so cheap. And since supplemental cementitious material is a byproduct of burning coal, the sources of supplemental cementitious material are going away. So we can co-sell our supplemental cementitious material and actually produce our cement for the same or even slightly lower cost than conventionally produced cement. So with that, thank you very much for this opportunity, and I'd be happy to take any questions, or feel free to email me at cody@brimstone.energy if you have any follow-up. I'll stop sharing my screen now.
Great. Thank you very much, Cody. That was great. Dive into some of the process emissions that come from heavy industry.